And now in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD of this rectangle is equal to 3 units in its length. Inside this rectangle we have those two semicircles. The radius of this big semicircle is equal to 2 units. The radius of this small semicircle is equal to 1 unit in its length. And our mission is to find out the length of this line segment AE. So first of all, we know that ABCD is a rectangle, and therefore all the angles inside this rectangle are right angles. So this angle is a right angle. This is also a right angle. This is a right angle. This is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle, this point as point P. Likewise, we will define the center of this big semicircle, this point as point Q. We will define the touching point of those two semicircles, this point as point S. We will define the point of tendency of tangent AE with this big semicircle, this point as point L. And finally, we will define the point of tendency of tangent AE with this small semicircle, this point as point G. In the next step, we will do a construction, that is to say, we will extend side CD of this rectangle, ABCD, and side AE by straight line until they touch each other. And we define their touching point, this point, as point F. We know that DC is one side of this rectangle ABCD. So DC is the side of a rectangle, it is absolutely a straight line. We extended the straight line DC by straight line, and the result is DF. When we extend the straight line by straight line, the result must be a straight line. Therefore, DF is a straight line. If you focus on the upper side of this straight line, DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. That says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF? Which angles we have at the upper side of DF at point C? We have this angle, it is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the small right angle ECF, we define this angle EFC as alpha. So, in the small right angle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right angle in the big right triangle ADF, this angle equals to alpha. This angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, the sum of the angles in any triangle is equal to 180 degrees. We have in this big semicircle the radius PL, that is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. Again, the radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. So here you can implement rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also here tangent AB that is tangent to this circle at this point, point M. In addition, we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius PL that is equals to 2. Again, the radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG that is equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we will prove that the big right triangle LPF is similar to this small right triangle GQF. Okay, so we prove that the big right triangle LPF is similar to this small right triangle GQF. So, why those two right angles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually, this is the angle PLF. In the big right triangle LPF, and it is equal to this angle, that is actually angle QGF. in the small right triangle GQF. So repeat again, we actually found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle GQF. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can find out that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to angle alpha as it belongs to the small right triangle GQF, it will be defined as angle GFQ. So again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So here this is angle LPF in the big right triangle LFP, and it is equal to this angle, that is actually angle GQF in the small right triangle GFQ. So repeat again, we found out that angle LPF in the big right triangle LFP equals to angle GQF in the small right triangle FQP, in the small right triangle GQF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually prove that all the triangles in this big right triangle LPF are correspondingly equal to all the triangles of this right triangle GQF. Therefore those two right triangles are similar to each other according to angle similarity rule. So when it is down, actually found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF according to angle similarity rule. Before we continue, we define the length of this 97CF as x. CF equals to x according to our definition. DP is the radius of this big semicircle, that is equals to 2. PS is also the radius of this big semicircle, that is equals to 2. Likewise, we have QS is the radius of this small semicircle, that is equals to 1. And finally, QC also, it is also the radius of this small semicircle, that is equals to 1. We continue with the similarity. We have found out that the big right triangle LPF is similar to this small right triangle GQF. And from the fact that they are similar to each other according to angle similarity rule, we will derive that the following relationship exists between their sides. We derive that side LP in the big right triangle LPF over side GQ in the small right triangle GFQ equals to side PF in the big right triangle PFQ over side QF equals to side PF in the big right triangle LFP over side QF of the small right triangle QFP over QF in the small right triangle GQF. Repeat again. We shall find out that side LP in the big right triangle or side GQ in the small triangle equals to side PF in the big right triangle over side QF in the small right triangle. LP is the radius of this big semicircle that is equals to 2 over GQ. GQ is the radius of this small semicircle that is equals to 1 and it is equal to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus 6. Again, PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So in total PF equals to 4 plus x. Over QF. What is the length of QF? QF in total equals to 1 plus x. Again, QF in total equals to 1 plus x. So we shall know that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x and we get that 2 times 1 plus x equals to 4 plus x. Here we'll open the brackets on this end of the equation and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation and we get that 2 plus x equals to 4. Here we subtract 2 from this equation and finally we get that x equals to 4 minus 2, that is 2. So we shall find out that x equals to 2 units. That is to say, 97 CF is equal to x equals to 2 units in its length. So write it down. In the next step, we will prove that the biggest right triangle in this drawing, that is ADF, is similar to the smallest right triangle in this drawing, that is triangle ECF. So we prove that the biggest right triangle in this drawing, that is triangle ADF, is similar to the smallest right triangle in this drawing, that is actually triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is triangle ADF, the big right triangle ADF, and it is equal to this angle, that is actually angle ECF, this one right triangle EFC. So repeat again, we can find out that angle ADF in the big right triangle equals to angle ECF in the small right triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. It is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD, and angle alpha equals to itself. So if we relate to this angle alpha, as it belongs to the small right triangle ECF, it will be defined as angle EFC. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So hopefully this is angle DAF. In the big right triangle ADF, and it is equals to this angle, that's actually angle CEF. In the small right triangle ECF. Repeat again, we can find out that angle DAF equals to angle CEF. Angle DAF in the big triangle equals to angle CEF in the small triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles in the big right triangle ADF are correspondingly equal to all the triangles of this right small triangle ECF. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually proved that the right big triangle ADF is similar. This is the sign of similar to the small right triangle ECF according to angle similarity rule. And from the fact that the biggest right triangle ADF is similar to the smallest right triangle ECF, we derive that the following relationship exists between their sides. We derive that side AD in the biggest right triangle ADF over side EC in the smallest right triangle ECF equals to side DF in the biggest right triangle ADF over side CF in the smallest right triangle ECF. So again, we derive that side AD in the biggest triangle over side DC in the smallest triangle equals to side DF in the biggest triangle over side CF in the smallest triangle. AD equals to 3 units in itself according to what is given as the question over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. What is the length of DF? DF in total will be equals to 2 plus 2, that is 4, plus 1 plus 1, so in total it is 6, plus 2, 6 plus 2 is 8. So in total DF equals to 8 units in its length. Again, DF equals to 2 plus 2 plus 2 plus 1 plus 1, in total is 8. So DF equals to 8 over CF. Here CF equals to 2 units. CF equals to X and X equals to 2. So CF equals to 2. So we shall find out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So 3 over EC equals to 4. We'll multiply this equation by EC, and you get that 3 equals to 4 times EC. Here we divide this equation by 4, and finally get that the missing side EC equals to 3/4. In terms of numbers, it is equals to 0.75. So this is the missing side EC, and it equals to 0.75 units in its length. What is the length of BC? What is the length of side BC of this rectangle ABCD? We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So BC equals to 3. What is the length of the missing 97BE? From the drawing, it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. BE equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. So BE equals to 2.25 units in its length. Right here, that BE equals to 2.25 units in its length. According to the sum rule that the opposite sides of an rectangle are equal to each other, we get that in rectangle ABCD, side DC must be equal to the opposite side AB. What is the length of DC? DC in total equals to 2 plus 2, that is 4, plus 1 plus 4, that plus 1 plus 1, that is 2. So in total, DC equals to 4 plus 2, that is 6. Again, DC equals to 6 units in this length. And according to the rule that the opposite sides of a rectangle are equal to each other, we get that AB equals to DC. DC is 6, therefore AB must be also equal to 6 units in its length. So in the next step, I'll copy the right triangle ABE in a new page and we'll implement the Pythagoras theorem on this right triangle ABE. Side BE equals to 2.25, and we just right now found out that AB equals to 6. The hypotenuse AB is unknown, so the hypotenuse AE is unknown, so we leave it as it is. So actually, this is the right triangle ABE. This is a copy from the original drawing. So here we have AB equals to 6, BE equals to 2.25, and the hypotenuse AE is unknown. Here we implement the Pythagoras theorem in order to find out the length of the hypotenuse AE. AE is the line segment that we are looking for in this question. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse this right triangle ABE is AE, therefore the square of the hypotenuse is AE square, and it must be equal to AB square plus BE square. So I write it down. In the right triangle ABE, the square of the hypotenuse, that is AE square, it must be equal to AB square plus BE square. So here AE is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in conclusion, we found out that AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. Here we take a vote out of this equation and finally get that the missing 97 AE is the 97 that we are looking for in this question. It is equals to the square root of 41.0625. This is actually equals to 6.408 units. And that is the answer to the question. So repeat again, we found out that the length of this 97 AE is 6.408 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this 97 AE. So in the drawing, we have rectangle ABCD. Side AD of this rectangle ABCD is equals to 4 units in itself. Inside this rectangle, we have those two semicircles. The radius of this big semicircle is 2. The radius of this small semicircle is 1. And our mission is to find out the length of this 97 AE. So first of all, we know that all the 4 angles inside any rectangle are right angles. So those 4 angles, they are all right angles. In the next step, we defined the relevant points for this question with letters. We define the center of this big semicircle, this point as point P. We define the center of this small semicircle, this point as point Q. We define the point of tendency of tangent AE with this big semicircle, this point as point L. We define the point of tendency of tangent AE with this small semicircle, this point as point G. In the next step, we did a construction. That is to say, we extended side BC of this rectangle and line segment AE by straight line until they touch each other. We defined their touching point, this point as point F. BC is one side of this rectangle ABCD, therefore it is absolutely a straight line. We extended the straight line DC by straight line. When you extend the straight line by straight line, the result must be a straight line. Therefore the result, DF, must be a straight line. And then, if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside the small right triangle ECF, we define this angle EFC as alpha. So this angle equals to alpha. This angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees. In 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the biggest right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Okay? So we have here the radius PL, the radius PL that is equals to R is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If A is perpendicular to LP, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. Likewise, we have the radius QG, the radius QG that is equal to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to the sum rule, all 1. So in this small right angle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right angle NPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that this big right angle LPF is similar to this small right angle GQF. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. That is a common angle that belongs to both sides. So we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the triangles of this right big triangle LPF are correspondingly equal to all the triangles of this small right angle GQF. Therefore, those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. I repeat again. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of this big semicircle that is equals to 2 over GQ. GQ is the radius of this small semicircle that is equals to 1. PF, actually, we defined CF as X. QC is the radius of this small semicircle that is 1. QS is also the radius that is 1. SP or PS is the radius of this big semicircle that is 2, and PD is also the radius of this big semicircle that is 2. So what is the length of PF? PF in total equals to 2 plus 1 that is 4 plus X. Again, PF in total equals to 4 plus X over QF. QF in total equals to X plus 1. So we can find out that 2 over 1 equals to 4 plus X plus 1 plus X. Here we multiply this equation by 1 plus X and finally found out that 2 times 1 plus X equals to 4 plus X. Here we open the brackets on this side of the equation and finally found out that 2 times 1 is 2 plus 2x equals to 4 plus X. Here we subtract X from this equation and finally found out that 2 plus 2x plus minus X is X. So 2 plus X in the side of the equation we have to only with 2 plus X equals to 4. Here we subtract 2 from this equation and finally found out that X equals to 4 minus 2, that is 2. So the length of this line segment CF is equals to X is equals to 2 units. In the next step, we proved that the biggest right triangle ADF is similar to the smallest right triangle ECF. And again, we proved that the biggest right triangle ADF, the biggest right triangle in this drawing, is similar to the smallest right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the angles of the big right triangle ADF are correspondingly equal to all the angles of this small right triangle ECF. And therefore, we actually proved that those two right triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AD in the biggest right triangle over side EC in the smallest right triangle equals to side DF in the biggest right triangle over side CF in the smallest right triangle. I repeat again, we will derive that side AD in the biggest right triangle over side DC in the smallest right triangle equals to side DF in the biggest right triangle over side CF in the smallest right triangle. AD is free according to what is given us in the question over EC. EC is the missing side, so we leave it as it is, and it is equals to DF. DF in total equals to 2 plus 2, that is 4, plus 1 plus 1, 4 plus 2 is 6, plus 2 is 8. So in total, DF equals to 8 units in its length. It is actually 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is 2, and 6 plus 2 is 8. Again, EC is the missing side, and CF equals to 2. So if we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So actually found out that 3 over EC equals to 4. Here we multiply this equation by EC and finally found out that 3 equals to 4 times CC. Here we divided this equation by 4 and finally found out that the missing side EC equals to 3/4 or 0.75. This is the missing side EC, that is equals to 3/4 or 0.75. What is the length of side BC of triangle ABC of rectangle ABCD? According to the rule that the opposite sides of a rectangle are equal to each other, we get that side AD in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So what is the length of the missing side BE? From the drawing it is very easy to see that BE equals to BC minus CC. Again, BE equals to BC minus CC. E equals to BC minus CC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total BE equals to 3 minus 0.75, that is 2.25. So BE equals to 2.25. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AB must be equal to the opposite side DC. DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2. So 4 plus 2 is 6. So DC in total equals to 6. And again, according to the rule that the opposite sides of a rectangle are equal to each other, we get that AB must be equal to the opposite side DC. DC is 6, therefore AB must be also equal to 6. In the next step, I copied the right triangle ABE in a new page and we implemented the Pythagoras theorem in this right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle ABE that I copied from the original drawing. This right triangle ABE, according to the Pythagoras theorem, AE square equals to AB square plus BE square. AE is the missing side, so we leave it as it is. And it is equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total, we have found out that AE square equals to 36 plus 5.0625. 36 plus 5.0625 is equals to 41.0625. So in conclusion, we have found out that AE square equals to 41.0625. Here we took a root out of this equation and found out that the missing side AE is equals to the square root of 41.0625. That is actually equals to 6.408 units. And again, in conclusion, we have found out that 9 cm AE equals to 6.408 units in its length. Okay, thank you very much.